Assalamu alaikum. I hope everyone is doing well at their places. So today we'll start with a new topic that is known as load flow analysis. In some books it is also written as power flow analysis. So what does this load flow analysis, and in what load flow analysis what we do, we actually analyze or we study the power system as is written on the first line. So it is actually used to find out the values of voltage, phase angle, reactive power, injected. I will let you know what does this injected mean at any bus. We assume that power system is consisting of a number of buses, and at every bus we want to find out these four quantities, that is voltage, phase angle, injected reactive power, and injected active power. So before going into the different techniques, what we do is first define it. So it is the solution of the electrical network under steady state condition subject to certain inequality condition under which the system operates. So it's actually the solution of the electrical network, that is the power system solution, and solution is nothing but getting voltage, phase and reactive power and active power. But the condition is, there are two conditions, that the system should be in steady state. In the previous chapters we discussed that transient or faults or something like which are abnormal condition, which are not a normal condition. But here we calculate or get the values of these four unknown quantities upon the condition, or we can say for the system which is in steady state. There should not be any abnormal conditions. And one more condition is that we know that we'll come to this, what is this inequality constants. There are some constants under which this power system operates. We need to find out these values under, so that these values fall under these constraints. Well, I will let you know what is injected reactive power, active power, and what are these inequality constraints. Okay, first I will discuss the inequality constraints. The first one is the voltage limit. Voltage limit should be, that means Vi, that is, I have written this I as the number of any, I can represent this I as the representation of any bus, arbitrary, where this I can change from 1 to n if n is the number of buses. So Vi minimum, or we can say this, the voltage that we get from this solution, it should be under this range between minimum to maximum. It should not go beyond this range. So this is one constraint. If for a good power system, you know that Vi minimum should be equal to 0.95 per unit, and Vi maximum should be equal to 1.05 per unit. So this Vi should be between 0.95 to 1.05 per unit, so that the voltage regulation is around plus minus 5%. Reactive power limit should also be within this limit, that is QGI minimum should be QGI should be between QGI minimum to QGI maximum, because this is usually for the generators usually have a maximum limit of generating the reactive power as well as active power. There is also a limit for minimum reactive power generation, because beyond that we might not have we cannot make excitation equal to 0. We can minimize it, excitation of this synchronous machine. Same is the case with the active power. If we go active power to 0, we may have to stop the machine, which is very difficult to do. So we can have some minimum generation and upon maximum as well, depending upon the rating of the machine. Also the phase angle, the difference between the phase angle of two buses. Here I is the ith bus, k is the kth bus. We can say 3 or 4 bus. The difference between these two phase angles should be less than the maximum phase angle that is prescribed, because we don't want this phase angle to go beyond certain value, because it has an adverse effect on the stability of the system. We will I told you earlier also that we'll discuss these things in that chapter, that stability. One of the students among you had asked me about the neutral grounding of the generator, and I told her that we'll be discussing in the stability of the system. So this will be also covered in that chapter. So what is the purpose of doing this load flow analysis or power flow analysis? It is used for designing a new power system. We assume that we have such a type of power system. It might have got this much of buses, and we have these lines, and after that, upon assuming these conditions, then we'll run the load flow and we see that what will happen to these four quantities, and if they are in the constraints, in the limits, we can say we have designed the power system. The line's length should be this, the line cross section should be this, the bus should be like this. The other things we can also design based on the power flow. So it is used for planning the extension of the existing power system for increasing load demand, as well as determine the best operating point of the existing system. Sometimes we have the power system, we just want to extend it, we just want to incorporate more or other part of the power system uh, just to just to have the just to meet the increased load demand. This is one, and another is that also we want to find a best operating point, because sometimes you will see that in optimization system we will see that what is the optimal power generation of a generator, because it is based on the fuel cost. So there is an optimum point upon which the generator can generate this active power. So we can find out that best operating point, or best what will be the optimized generation of active power generation of the synchronous generator. Sometimes we just want to decrease the losses of the transmission line. In that case, we can have that constant, we can say that objective function. We can do that and have different types of voltages, reactive power, delta, and in that case, we minimize the power losses. And to have calculate the voltages with reactive power, active power, delta, so that we have minimum loss. So we can say that point is known as best operating point. This is also done to do to find the best operating point. So these are the two main purposes. We can see three. One is designing of new power system. One is the planning, the extension of existing power system, and find the best operating point of the power system. So this is what why this is this is why we do with the load flow analysis. Now, what are the information that we get? We have a little discussed in the beginning that we find four bus quantities: injected active power, it is denoted by I; injected reactive power, it is denoted by QI, this is PI; magnitude of the bus voltage, that is VI; and phase angle with respect to some reference. Definitely, this is always with respect to some reference. So first we'll discuss what is the injected active reactive power or injected complex power. Now this is usually the ith bus including this. So here we have some load demand and it is connected to a generation. So this generation is supplying some complex power denoted by SGI, and this load is getting some load or demand, that is SDI, from this generation. So this is the transmission part. In this case you will see that some part of this complex power may go to this transmission if this is more than this, definitely. So we can say this power, this complex power, which is actually the subtraction of this and this, is known as the injected power, or sometimes transmitted power. So this SI that is given by this will be simply equal to SGI minus J times, sorry, it is not J, it should not be a J, it should be SDI. So the complex power that is transmitted, that is injected into the bus, will be equal to the generation complex power minus load demand complex power. That is what is meant by this. Here it is not, J is not here. So SGI itself is equal to PGI plus JQGI. That's the complex power generated at the ith bus. That is what this I means. SDI will be equal to PDI plus JQDI. That is the complex power demand at the ith bus. Now SI this J is not again here, is equal to SGI minus SDI. You can see I haven't written J over here. This SGI will be equal to PGI plus JQGI minus PDI minus JQDI. So I will separate the real and this imaginary parts. This is the real part, that is PGI minus PDI. Again, this QGI, G times QGI minus QDI. This can be calculated as injected active power, and this will be injected reactive power. Also, currents can be, we can use the KCL at the ith bus. It will be I will be equal to IGI minus IDI. The phase angle can be written as delta I will be equal to angle of the VI minus angle of V reference. So magnitude of A, the bus voltage magnitude at the ith bus. So here we can first define what is the significance of VI. You can see that reactive power flows from higher voltage bus to a lower voltage bus. You also already know this. And significance delta will be real power flows from leading bus to the lagging bus. That means, or from the bus having a higher phase angle to a lower phase angle. This is the significance of VA. But these two things will be, or these two conditions are true only when R by X ratio for a system is very low. That means when X is more as compared to R, or when R is low as compared to X. This is true for our transmission system, but for our distribution system, this is true in other way around. That means in that case, R by X ratio is very high. But in transmission system, this is true. You will always see these kinds of things happening because transmission system has low R by X ratio, and in that case, you will see that higher voltage reactive power flows from higher voltage to lower voltage magnitude, and real power flows uh, from the higher phase angle bus to the lower phase angle bus. So this is about the physical significance of VI and delta I. And this was, you can see from here, this is the information of the stage. First we get the four bus quantities, and after stage second, when all the four bus quantities at each bus is known, then we find the line flows and the losses occurring in between the lines connecting the two buses. You can see I have, this is the ith bus, this is the kth bus, this is SIK, that is the complex power that flows from bus I to bus K. This may be called as SKI, that is a complex power that flows from K to I. You will see if the system is lossless, they will be same, but if there is some loss, they will be different, and that difference will be the loss in this transmission line. So from here we can get line flows, that is the complex power that is flowing through the line, and the losses that is occurring in the line. In this case, you will see that we usually say that reactive power is not lost, but here some reactive power will be stored in the line, that is also taken to be the loss. So here there will be reactive power loss as well as active power loss. In load flow analysis, following points need to be considered. The first one, that generations are represented by the complex power, complex sources that we have already seen. That SGI is equal to PGI plus JQGI. Here it should be load demand. I have written as like generation. This is load demand are represented by the complex load demand, that is SDI is equal to PDI plus JQDI. The transmission line connected to the ith bus are replaced by their pi equivalent circuits. These three are very important, and we are keeping these 3 points in mind while doing the load flow analysis. Before going into the load flow analysis, we first form the Y bus. What is Y bus? We'll come to know what this Y bus means, and it is very important for doing the analysis of the load flow. This is our 3-bus system. This is one bus, this is bus 2, this is bus 3. This is the current that is injected from the source. Let's say this is source 1, source 2, source 3, and I have represented all these lines by a pi equivalent. You can see this by pi equivalent of this, pi equivalent, pi equivalent. Sometimes these may be discarded if the transmission line is short transmission line, but in general I have shown it like this. So we can use the KCL at this point. This I will be equal to current flowing through this plus current flowing through this. You can see current flowing through this will be equal to current flowing through this will be equal to V1 minus V2 divided by the impedance. Since I have kept it as admittance, it can be multiplied V1 minus V2 into this admittance plus current flowing in this parallel branch, that is V1 into Y120. That's what I have written over here. In this line we have two parts of the current. One is in this line, bigger line, another is the parallel line. So V1 minus V2 into Y12 plus V1 into Y120. Similarly, we can have two components of the current, two terminals in the current. One is flowing through this bigger line, another through this parallel line, that is the shunt admittance. So this will be equal to V1 minus V3 into Y13, that's what I have written over here, plus V1 into Y130, V1 into Y130. So then I have taken V1 common and taken the terms of V1 to be like this. So it will be V1 into Y12, then Y120, then Y13 and Y130. Then I have written V2 and V3 separated. It's minus V2, Y12 minus V3, Y13. So this is for this case I1. Similarly, I2 can be calculated from here. I2 can be calculated by using the similar explanation. I have written I2 and I3 directly. You can calculate it on your own. I2 will be minus V2 Y12 plus V2 into Y12 plus Y23 plus Y120 plus Y230 minus V3 Y20. Similarly, I3, they can be calculated like this. These are the equations 3 which actually gives us the source current that is flowing into the bus from the actual source. So I can, this equation 1 can be written as, equation 1 is this one. It can be written as I1 is equal to V1 Y11 plus V2 Y12 plus V3 Y13. Okay, so I have written it like this, where Y11 is actually this quantity, that is Y12 plus Y13 plus Y120 plus Y130. It has to be like this. Similarly, Y12 will be equal to minus Y12. I have consumed this minus into this Y12. Similar, this Y13 is equal to minus Y13. So this is the some modification of this equation into this equation. This is equation 4. It's not equation 4. This is equation 4. That is V1 Y11 plus V2 Y12 plus V3 Y13, and Y11 Y12 and Y13 are represented by these three equations. Equation 2 can also be written as I2 is equal to Y21 plus Y22 V2 plus Y23 V3, where Y21 is equal to minus Y12, which is equal to minus Y12, Y21 and minus Y12. It is same. Y22 is the summation of these 4 quantities, which is actually this quantity. Similarly, Y23 is equal to minus Y23. It is equal to this quantity along with the minus, so that it is consumed over here. You can see here Y12 and Y21 will be similar. That is, the admittance of the line between 1 and 2 will be same as that between line 2 and 1. That is what this equation means. So I3 can be written as like this, and similarly we have these 3 different quantities. We uh, describe it like this. Here I have used the small letter y. Here in this equation, these 3 equation 4, 5, 6, I have written the capital letter y. So equation 4, 5, 6 can be written in terms of matrix as this is equation 4. You can see it. Sorry, this v1 y11 v2 y12 v3 y13, and then this equation and this equation we have I1 I2 I3 y11 y12 y13 y21 y22 y23, and then this like this. So this can be written as like this, and in the compact form this can be represented by I, where this I is 3 cross 1 matrix. You can see it is a vector, and this Y, it is a 3 cross 3 matrix here, and V, this is I bus, this is V bus, bus voltages 3 cross 1. Why this is Y is Y bus of the power system. Actually we are interested to find this Y bus. So Y bus is nothing but Y11 Y12. It is like this, and it is defined by these 9 equations. That is, first these 3, and then these 3, and then these 3 equations, and in compact form it is written like this. Now coming to this, we know that y1, I will define it again, and I will So what is it known as? This y1 is equal to y12 plus y13 plus y120 plus y13. It is known as short circuit driving impedance or admittance or sum of all admittance connected to bus 1. So in general, I can write as YII sum of all admittance connected to bus I. Y12 is minus Y12 minus times total admittance connected between bus 1 and 2, or in general Yij is equal to minus Yij, that is minus times total admittance connected between bus I and J. So you can see it is the total admittance connected to bus 1. You can see it from here. The total admittance connected to bus is Y12, Y120, Y130 and Y13. That is this admittance. So by doing this, by we can see defining these elements like this, it is very then simple to calculate the y bus. So we can generalize the matrix in equation 7 to the n bus system. Now this is the equation 7. We can generalize to n bus system. We can uh, instead of going to stopping at 3, we can go up to n like this. We can go up to n like this. We can go up to n. We can go up to n. You can see I can generalize it like this. So I1, I2 digest up to In, Y11, Y12 digest up to Y1n, Y21, Y22 digest up to Y2n. Similarly, up to Yn1, Yn2 digest up to Ynn. It will be V1, V2 up to n. This factor will be of the order of n into 1. This will be n into n. This will be n into 1. In compact form, I will be equal to of order n cross 1. This is n cross n. This is n cross 1. Now I'll write down the equation 4 and 5 again just to have some more important things to discuss. I11 is equal to V11 Y11 V1 plus Y12 V2 plus Y13 V3. This is equation 4, 5, 6. We can extend this. We can get these equations from this system also where we can define n is equal to 3. So you can see it from here. This I1 is equal to, I can represent it by a summation. I can run this j from 1 to 3 because here there are only 3 terms. Summation will represent these two sums. And y here you can see this one is variable 1, 1, this 2, 2, 3, 3, and this one is constant 1, 1, and 1, and 1. So I1 will be equal to the summation from 1 to 3 v1 y1j vj. Similarly I2, it can be represented by the summation of from j is equal to 1 to 3 v2j vj. Similarly I3 can be represented v31 v1 plus v32 v2 plus v33 v3, and it can be represented by summation of from j to 1 to n 1 to 3 y3 j vj. So okay, I can represent this all the three equation in one equation like this. I can write this I is equal to summation of j goes from 1 to 3 yij vj, where I has the values of 1, 2, and 3. When I is equal to 1, you can see that it will be I1, same y1j vj, that is this equation. When I is equal to 2, it will be I2, summation j is equal to 1 to 3 y2j vj, it is this equation. Similarly for 3. So this equation can be written for an n bus system and generalized for n bus system like this. I1 is equal to y11 v1 plus y12 v2 plus dash y1 and vn, and this will be this value. Similarly I2 can be this I it's in between this from 1 to n. This I can be take value from 1 to n. I will be like this, and In will be this value. In general, I can represent this I will be equal to summation j is equal to 1 to n yij vj. Here this I is also from 1 to n and j is also from 1 to n. This is the generalized equation for an n bus system where II is represented by this. This is an important result. Okay, I will stop here and I will start next important thing in the next class.